we didn't quite finish with dark atoms. And what was left is some of the amusing applications. So there's one you might have, you already mentioned the pick up your certificates of attendance?
Yeah.
Okay. So one you might have noticed in the literature was by Lisa Randall and collaborators at Harvard, that they called double disk dark matter. And the idea was they would have some minority component of the total dark matter being dark atoms, because they didn't, because typically if you had such strongly interacting dark matter, it would violate the bullet cluster bounds. But they wanted some fraction, say around 5% of it or 10% to be 10% of the dark matter is atomic dark matter. And then what they assumed is that just like ordinary baryons, the dissipated interactions of the dark atoms would make them fall into the disk. And so you would get a dark disk which is overlapping with the visible disk of the galaxy. And so, and there were various things that were, for instance, they believed that you could explain some periodic increases in cometary comets passing through the galactic plane. I think there was some geological evidence for this, and Lisa was relating it to extinction of the dinosaurs and whatnot. But whatever signals like that you might be motivated by, you can constrain this using data from Gaia, which would be, so I guess maybe the transverse motions of stars which are going through the disk are going to be sensitive to how much matter is there, and if there's a dark disk, there's more there than we typically assume.
Would the dark disk have the same core cost problems that the baryon disk does?
Well, this core cusp thing is a feature of the halo, and the disk is a separate component. So I think we wouldn't normally consider a cusp within the disk component. It's not something, I don't think that would be easily measurable.
I think, sorry, I didn't phrase my question very well. What I meant was the core cusp problems that come from the halo, does the dark matter disk contribute to those problems?
I think they are unrelated.
Okay.
I haven't thought about it. Anyway, so what you get constraints on is the surface density of dark matter in the disk. So that's a density of dark matter per unit area. And they model the disk, they model it as something with some thickness. And so typically, the constraints you get are a function of the assumed thickness. We don't know, but one can then model it. And let's see, I thought I wanted to show that next figure. Yes. Marked down here. But yeah, so this is showing the surface density versus thickness of the dark disk, which they were wanting to explain these cometary periodicities. So some of the works that I mentioned that have been using Gaia data have now surpassed that. This work that was Caitlin Schutz and collaborator, now they've even been surpassed to limits like so. So it's not a very likely prospect, or at least it's highly constrained. And in fact, in making these predictions, they just assumed that all of the dark matter would collapse into a disk. They didn't try to model the structure formation. And some people, can you scroll down to this one? Some people actually modeled the structure formation. And what they found is that these dark disks in a simplified dark atom model where you don't have the whole mirror sector, you just have dark atoms, that typically in the parameter space of the dark electron mass and the coupling, the gauge coupling, you just get small regions, these blue regions where you can actually form a dark disk, and otherwise they get disrupted by gravitational, like dense subhalos passing by disrupts them. And so it's actually unlikely to get a dark disk in the first place. These people showed in a simplified dark atom scenario. Thank you, Marco. So that was one application. And another one that people have talked about is formation of early formation of supermassive black holes. So by supermassive, we mean 10 to the 9th solar masses. And by early, we mean redshifts around 7 to 8. So a few of these things have been observed, and they're puzzling to standard lambda CDM because structure doesn't form soon enough to make such big objects that early. And there's a limit on how fast black holes can accrete. It's called the Eddington limit. And so people have calculated that you would need to exceed this limit in order to grow such large black holes that early. And the idea of using dark atoms is to use the dissipative interactions of dark atoms to cause gravothermal collapse. There's something called gravothermal catastrophe, which it actually goes back to the theory of globular clusters. Lyndon Bell figured out that this is the mechanism that forms a globular cluster. And the idea is you have some gravitational potential well. So say we're talking about we're talking about a proto-halo that's going to develop into a galaxy. And now suppose you got dark matter particles scattering with each other in the presence, in the vicinity of this potential well. And suppose you slow down one of these dark, so it's a dissipative interaction and you can lose energy. And suppose that you slow down one or more of those particles so that they get trapped in the well. And then what happens is the potential well gets deeper. And so then this turns out to be a runaway process. And this can lead to the accelerated growth of black hole formation earlier than you would have expected from the standard non-interacting cold dark matter. And so can you show the figures again? A few people have worked on this, including next figure. Yeah, including my former student and postdoc. And so they did a gravitational n-body simulation with dissipated dark matter interactions put in. And here's the parameter space of interest. There's the dissipated cross-section per unit mass. And this F is the fraction of dark matter which is in these strongly, it's like the Randall scenario. It's just a fraction of the total dark matter that's dark atoms. And so there is a degeneracy. You could explain these three black holes anywhere along this curve, depending on how much accretion you think occurred. You need a little bit of accretion. These blobs are showing you successive E foldings of accretion. So like for this one, if with just one or two E foldings of accretion after the initial black hole collapses, then you could explain the observations at a redshift of around 8. And you see, this is not a huge cross section. This is like 10 to the minus 0.7 centimeters per gram. That's a bit smaller than what we were talking about before in terms of the lid cluster, etc. But because it's a dissipated interaction, it works very well for this effect. Oh, and interestingly, you can also make it work even if the dark atoms are all of the dark matter, so a fraction of equal to 1. You can get it to work with. So that was.
Question in the chat.
Yes.
Is this expected to occur in early protohalos that are thought to form first population 3 stars?
That are expected to form population 3 stars.
Yes, you want to speak up and complement the question?
Yeah, sorry. So just about the this black hole formation mechanism that you're talking about. So is this expected to occur in the, the high redshift halos around, 25 to 30, where we expect, the first population 3 stars were formed?
I'm not sure. I'm not sure if those coincide with where these supermassive black holes are observed. This is really out of my field, so I don't think I can tell you.
Okay.
Thanks. Another application, you've heard of this 3.5 keV X-ray line that's coming from galactic clusters and on the Andromeda galaxy, I guess. Have you heard of that? It's one of these anomalies that maybe it's real, maybe it's just some ununderstood transition line. But anyway, a lot of model builders have tried to explain it with, say, 7 keV neutrino decaying to photons. But you could also get it from the hyperfine transition in dark atoms. So, the transition where you go from spin triplet to spin singlet, that's the hyperfine transition is. And I wrote down the formula for the energy. It's a small energy compared to the other scales, of course, and so you can tune parameters to make that work. I don't want to go into the details of that. I just wanted to mention it. And finally, I wanted to go back to the structure formation. And well, the thing that motivated the study I'm going to mention was the question of, could you have dark planets, stars, maybe even life in a perfect mirror sector? So here I'm talking about not a simplified dark atom. Yes.
I just have one quick question about the 3.5 keV.
Yes.
Thanks. Would that require a model with some serious fine tuning to get that hyperfine transition exactly right at that 3.5 keV line?
No, I mean, it's just one piece of data that you're fitting. So I wouldn't call it fine tuning. It's just matching your theory to an observation.
Okay.
And you can do it with relatively natural values of parameters. So yeah, I don't think it looks particularly contrived. Yeah, so I got interested in this question because normally we assume that well, dark matter might be complicated, but it can't really be that complicated, right? But if it's an exact mirror sector, then of course it would be that complicated. Is it possible? And so in this model, you only have, well, in the simplest version of this model, you only have two free parameters, which are environmental parameters, because all the physics, microphysics parameters are exactly the same as in the standard model. So the two free parameters you have are the one that we mentioned before. What's the mirror sector temperature compared to the standard model temperature? And then there's the other one that we've mentioned, which is the fraction of, well, we called it fraction of interacting dark matter, but this would be the fraction of dark atoms compared to normal atoms. Okay, so here again, we're assuming that dark matter is not all of the, dark atoms are not all of the dark matter. They're going to be some fraction. And well, I'll show you in the next slide that what the bounds are on that fraction. So this was worked out by my student, J.S. Rue. And he did the same kind of structure formation calculation that I referred to previously by those authors who just worked on simplified dark matter. He did it for the whole exact mirror sector. And those are the two parameters. That's the temperature ratio, and beta is related to this. It's just the fraction of dark atoms compared to normal, the ratio of dark atoms to normal atoms. And so you see that ratio, it has to be somewhat less than 1, but not 0.8 or so. And the various constraints are from just ways that you would look for dark mass, increased mass to light ratio, like gravitational lensing, macho searches, etc. And so this is the limit, and you see the limit, it gets stronger as you make the dark sector temperature higher. It can only be as high as 0.5, if you recall from the last lecture. But if you make it lower, then you could live with, so this would correspond to 14% of all the dark matter being in dark atoms. And so it's less matter than what's in the visible universe, but it's enough that there could be things there. We weren't able to go into the details of will you really get stars and planets? We just know what the constraints are on these parameters, but it's likely that you could have formation of these kind of structures that would end up in our disk. Yes.
This is kind of a crazy thought experiment, but if a dark species existed and they were looking for, the missing, whatever it is, 15% of matter that they don't see, would you imagine that their experiments would in some way be opposite to ours?
Well, wouldn't they be doing the same kind of experiments as
I guess that's what I'm
us,
wondering.
just with different parameters and different expectations? Anyway, that's pretty speculative. Okay, so we talked about dark atoms for a long time now, but we're still supposed to cover other kinds of composite dark matter. And so let's see how far we can get. So now I'm going to go to confining gauge theories. Mostly I'll think in terms of SUN because that's what we know in the standard model, but you could also have SON, SPN, confining gauge theories. And the simplest kind of dark matter you could have in such a theory is just blue balls. So if you only have gauge bosons in the hidden sector, no dark quarks, then you're going to have blue balls. And in the absence of mediators or connectors to the standard model, of course, they're going to be the stable particles in the dark sector. We know what their mass should be, at least in the case of SU3, because lattice gauge theorists have studied this. And they find that the lightest blue ball should have a mass of 1750 MeV in the standard model. And so if you work out what does that compare to the scale lambda QCD, by some definition of lambda QCD, it's around 7 times. And so now we could imagine in some other SU3, dark hidden SU3 sector, since lambda is the only, I should mention this, what are the parameters describing such a theory? So actually there's just one. I'm going to call it, we can call this SUN prime, and I'll call the analog to QCD lambda prime. So this is the confinement scale. It's something that we use instead of the gauge coupling because you know about dimensional transmutation. There's some relationship to the gauge coupling, but this is really the more physical quantity to consider because the gauge coupling is running, whereas this is one number that you can quote to characterize the strength of the interaction at a given energy scale. So anyway, we could expect in a theory with some other confinement scale that's the lowest blue ball mass, which incidentally, this is the spin 0 blue ball with quantum numbers, positive parity and positive charge conjugation. Let's go to the figures and look at the whole spectrum because there's a spectrum of blue balls. So this is what the spectrum looks like in SU3. This R0 is something which goes inverse to the confinement scale. And so you see they've worked out these spectra for the various quantum numbers. 0 plus plus is lowest. Usually that's the one we worry about. I'll show you an example where people also worry about this one. So that's the case for SU3. It's also known in the large N limit of SUN. Here's the spectrum. Now the masses are plotted along here, the angular momenta versus angular momenta. So all these Reggie trajectories. And now they've labeled the quantum numbers by these dots and colors. But the point I want to make here is that this is the n goes to infinity limit of SUN. And it's not, if you compare the numbers, it's not that different from this picture. So 3 is big enough compared to 1, so that at large n, there's no dramatic scaling. Reach a nice limit, and therefore this coefficient here, this is going to be some weakly, this will depend weakly on n, but not very importantly. Yes.
Does the mass scale linearly with the confining scale for all of these confining gauge theories?
Say it again.
Does the mass scale linearly with the confinement scale for
Oh.
all of these gauge theories?
Yes. Yeah, because it's the only, I mean, it's basically dimensional analysis. There's nothing else it can be.
Okay, thanks.
I'm sorry, on that plot, on the left y-axis, you had that r times mass, and on the right axis, yeah, so how do we know the confinement scale lambda prime to write this right axis?
This one?
Yeah. and then
Yeah,
compare
R0
that.
is just a definition. So the lattice gauge theorists, they like to use some other parameter which it's related. I mean, so there's some number here of order 1, which I'm not telling you, but
And why is it order 1? We're just assuming.
it's just a definition.
Okay.
Yeah, I mean, the lattice gauge theorists, they like to use various different quantities for making dimensionless quantities. In this case, they plotted m squared versus over the string
Oh, no,
tension.
I'm sorry. So on the left axis, you have this R naught times mg, and then on the right axis, you have this mg indicating to me that you know lambda prime.
This mg,
Correct.
oh yeah, because this is QCD. So they do know lambda prime
Ah,
for QCD.
oh,
Yeah,
okay.
so yeah, this is in the real world. This is what you could
I
use
see.
if you wanted to convert to some other
Sure.
lambda prime.
Thank you.
Sure. Okay, so how do you get the relic density of blue balls? Well, so one thing you could do is to introduce some kind of portal that would allow them to decay or annihilate. I mean, suppose you wanted to do thermal freeze out, but you'll soon realize that it doesn't work. Well, just write down some portal interaction. Here, I'll write it in terms of the gluon fields. So these are the gluon field strengths in the sector. And now we can just couple that to any old standard model gauge invariant operator. For instance, well, that's not really gauge invariant without the Higgs, but we could always put the Higgs in here and make this one higher dimension. Let me just write it this way for simplicity. And then this singlet operator is something which would interpolate between the vacuum and a glue ball state. Here, let me call the glue ball state phi. So this is going to be some number, or some form factor. But in any case, you see what this interaction will do is it'll allow the glue ball to decay into standard model fermions. Of course, it will also allow glue balls to annihilate. This is the diagram I want. Well, you know, something like this, say. But the point is that if you have decays, they're typically more important than annihilations. And so it turns out that you will never get this to be a big enough cross section for thermal freeze out, because if you do, then the decay rate will be too fast. So I don't want to spend time on it because we don't have much time, but the point is that decays always dominate over annihilations. And so you don't get the usual thermal freeze out mechanism for glue balls. It doesn't work unless you choose ridiculous parameters for their masses, like KeV scale and tiny scale, sub-eV scale for the confinement scale. Yes.
And why would that be an unreasonable choice?
Well, if the confinement scale is less than an electron volt, there's nothing to annihilate into that's light enough. Well, maybe neutrinos, but anyway, it looks very peculiar. So what do I want to say here? Oh yes. So instead, what one could do is to assume that the glue balls just get created during the confinement phase transition. Okay, so when the temperature of the dark sector falls below the confinement scale, then you're going to go through this confinement phase transition. And so a simple calculation you could do is to just assume that the energy density in gluons gets converted into energy density of blue balls at that temperature. And then you can use that to estimate the density of blue balls after the phase transition. So that's a pretty straightforward calculation, and I'll just quote the result. You get some big number, 10 to the 8th. And then there's this ratio of the entropy in the dark sector to the entropy in the standard model sector. And it scales linearly with the confinement scale. Okay, so this thing, 2 spins, n squared minus 1 colors of gluons. That's the temperature ratio. This is just the ratio of entropies between the hidden sector and the standard model at the time of this phase transition. So you see it's a big number here, and if you want this to be order 0.1, then you have to compensate either with a very small confinement scale or a relatively small dark sector temperature. Since you got a cube here, it doesn't have to be ridiculously small to overcome that 10 to the 8th. Okay, so that's kind of a 0th order estimate of the glue ball relic density. But yes.
In this part of the estimate, are we assuming any interaction between the standard model and the dark sector?
None at all. So it's just a secluded thing here.
Okay.
And but there's something else that can still happen. And this will be familiar to you from the SIMP mechanism. Can you guess what I'm going to say? What is the SIMP mechanism? 3 to 2, yes. So this is feasible for the glue balls as well. We can have 3 to 2 annihilations. And so these will further reduce this estimate somewhat. It turns out to be not a hugely dramatic effect, but it's something that you should take into account. And how would you calculate the cross section for that? Well, there's an estimate you can do for the glue ball self-interactions using something called naive dimensional analysis. Going back to Howard Georgi and company. It's kind of a rule of thumb for knowing where to put in factors of 4 pi when you're talking about a strongly coupled system like mesons and baryons and QCD. And then there's large n scaling, which was figured out by Witten originally. And so this gives you some kind of parametric prediction of the self-interactions of the glue balls. And it turns out to be like this. So we're summing over powers of the glue ball field. And you get factors of 4 pi over n to the little n minus 2. And there's the mass of the glue ball to the 4 minus n to make the dimensions right. So this is the coefficient of the endpoint function of the glue balls. And well, this 1 here, it's really some number of order 1. So we don't know that. It's just a kind of order of magnitude estimate. Anyway, you could use that for the case little n equals 5 to figure out what this 3 to 2 amplitude is supposed to be. And well, no, I'll come to that. So, yeah, so the relic density of glue balls, it's sensitive to the initial condition, the initial conditions of the universe. This psi, I mean, if I had an inflaton that didn't couple at all to the hidden sector, then you would think, oh, I'm not going to get any glue balls. But one interesting thing is that you can never completely decouple such a sector because there's always gravity. And it turns out the gravitational production can be non-trivial. So if we have standard model particles annihilating into graviton, then we can form these hidden gluons. Even if we started off with absolutely 0 temperature in the hidden sector, I'll put a prime on these to remind us that they're hidden gluons. And so the relic abundance of these hidden gluons turns out to be 10 to the minus 6 times the number of gluon colors. In this case, it's dependent on the reheat temperature. So, it depends on how much energy was available in these collisions, and this is to the power 3. So now instead of being sensitive to the initial temperature of the dark sector, it becomes sensitive to the reheat temperature after inflation. And so I'll go to the slides, Marco, to show you a picture of what these authors found. Michele Reddy and collaborators. So in the plane of the confinement scale and the reheat temperature, they find you want to be somewhere along these curves in order to get the right relic density. And there's different regimes depending on how it does depend on whether the gluons were able to thermalize. So if the reheat temperature was very small, the gluons start out with such a low energy that they don't ever have time to thermalize before the phase transition happens. And then the thermal history becomes sensitive to how many dark glue balls do you get per gluon. It's like at the LHC, it's like injecting a very high energy gluon and letting it hadronize. It might produce 100 hadrons, or it might produce 30. So depending, they don't know, they just parameterize it. So they get different curves. If the gluons thermalize before the confinement phase transition, then you get a definite prediction. And here, this interesting little shift here is the result. So in this case, the 3 to 2 interactions did not come into equilibrium. Here they did, and you see the small shift that happens. So that's underscoring my statement that the 3 to 2 annihilation, it's not a huge effect. Okay, I think well, thanks, Marco. Another possibility for so something a little bit beyond pure glue balls is a mixed dark matter sector where you have axions and glue balls both participating as dark matter candidates. And this is a rather natural thing to happen because you know how axions like to couple to yes.
It's about that plot that was just being showed. Thanks, sorry, Marvin. Okay, so as I understand it, temperature is increasing, so our time is moving from right to left.
No,
on
there's
this
no
plot.
time. There's no time there. That's the reheat temperature. So it's a
Oh,
parameter.
okay, so I guess I'm a little bit confused then about, we're saying confinement is happening before thermalization. There seems to be some kind of time.
Well, what I was
Comparison.
trying to indicate was that if you have very low reheat temperature, then the energy of the gluons before that confinement transition is such that they don't efficiently thermalize. It's a non-thermal distribution of gluons. So essentially, they have much higher energies than they would if they thermalized. So there's many fewer of them, but much higher energies than if they thermalized.
Okay, that helps, thank you.
You're welcome. Yeah, so a typical coupling of axions is to, sorry, this is a GG dual. And so it turns out that in this scenario, you can adjust. So remember, before we were saying everything just depends on the temperature ratio. Here, this is the decay constant of the axion. Here, now, it turns out that the relative production of glue balls versus axions is going to depend on the combination of these two parameters. Can we go back to the slides? Next slide. And yes, these authors have parameterized it in terms of the can you scroll down? I'm trying to remember. Let me look at my version to see if I wrote it properly. I'm forgetting what TVMSC. Photon temperature. Oh, yeah. It tells you it's the photon temperature at the time of the confinement transition. This is the axion mass. And what they work out is that, so in this whole plane, you get the right Rayleigh density, but if you're in the blue region, then you're dominated by axions, and in the red region, you're dominated by glue balls. And these contours tell you that R is what they use for Xi. So these contours tell you the values of Xi and of axion if you wanted to be at a certain point in this plot. And there's a certain function that gives you equal parts of dark matter. I mean, equal parts of blue balls and axions. So I just wanted to mention that scenario. We can go to, you can turn off the slides again. And I also wanted to mention the self-interaction issue, the one that I was talking about for solving small scale structure problems. So if you remember back to that blue ball potential I wrote down with the B of phi, you can read off from that what is the amplitude for, so we're talking about 2 to 2 elastic scattering here. So you can read off what the amplitude is and work out what's the cross section. And it's 12 pi cubed over n to the 4th mass of the blue ball squared. And so if you match that to our fiducial number for getting solving the small scale structure problems, then you would make a prediction that the glue ball mass should be around 130 MeV, depending on the value of n of it. So this is for sigma of order of Barn per GeV. Okay, so you're interested in rather light blue balls if you want to use them for this purpose. But remember, yes.
Why does sigma go like 1 over n to the 4th there? Where does that 4th power come from?
It comes. Oh, wait a minute. Did I solve this wrong? Because okay, the thing that you're interested in. So sigma over m would go like in cubed here. And so if I set that to something and if I solve, yes. So this is the thing, sorry, it's sigma over m, which is the figure of merit. So now if I solve this thing for, if I turn this around and solve for the mass of the gluon, then I get n to the minus 4/3, right?
Yes. Mhm. Okay, thank you.
Well, thanks, you helped me catch my mistake there. But you remember last time I was kind of emphasizing that this is an issue which is still not completely settled, but many people prefer to have a velocity-dependent cross-section because of this thing. We were saying that clusters of galaxies have less coring than small dwarf galaxies. And so here you don't get that. You just get a constant as velocity independent. But there's another elaboration of blue ball dark matter, which is also rather natural, that lets you overcome that problem. And that's if I would think about supersymmetrizing it, or if you don't like supersymmetry, just imagine that there's another particle, which is fermion, that's also in the adjoint of SUN. So we have the gluon, and we have, I'll just call it a gluino. And now these can form a bound state. I'll call it phi twiddle. So this is also a stable bound state. And some people call it the blue ballino. So that could also be a dark matter candidate. And suppose that we make this, suppose that we assume that this is a heavy particle. So that if the gluino is heavy, then the blue ballino is going to be much heavier than the, let's say that m phi twiddle is much greater than the mass of the glue ball. Well, then the glue ball can be a light mediator, and the glue ballino can be the dark matter. And we could put in some portal to the standard model to make the glue balls decay. Let me write that. So suppose that the glue balls are unstable, but that portal would not typically lead to the glue ballino also being unstable, because that's a different particle than the one that we would need to write for the glue ball portal. So then we have diagrams like this, where we have exchange of a light blue ball. And so this would give rise to velocity dependent scattering. The blue ballinos. Not only that, but it would give us an annihilation channel, because the blue ballinos would annihilate into the light blue balls. And then I'm assuming that these are going into later on the standard model. And so that means that you could use this to get thermal relic density also for the blue ballinos. And another interesting thing is that these are very strongly interacting composite particles. They can have a very big cross section, a cross section so large that it can violate the perturbative unitarity bound, which is that gives you a bound like a few TeV, right, for dark matter mass. And so it turns out that the mass of the blue ballino could be at the PeV scale. So that's kind of interesting. It's above the unitarity bound, but it doesn't violate the unitarity bound because that's for elementary particles. Yes.
Thanks. Why does that scattering have to be velocity dependent?
Oh, so if you assume that this is a light particle, then it will be velocity dependent. Whenever you exchange a light particle, you understand the opposite limit. If it's a very heavy particle, I can just shrink this propagator and it becomes a point-like interaction. Then that gives you isotropic scattering, which is part sphere scattering. It's not velocity, it's just a constant cross section. Whenever you exchange a light mediator at low velocities, you will typically have low momentum transfer, and so you'll have a bigger propagator and stronger scattering. And then, since we talked about mediators making the glue balls unstable, that gives you lots of opportunities for indirect detection, which we didn't talk about a whole lot so far. So if we have portals, get indirect signals. An example, so we can have the portal to the standard model hypercharge field strength. Here's the corresponding operator for the hidden sector. And you see what this would do. It would allow the glue ball to decay into photons. And of course, there's strong constraints on gamma ray telescopes. Look for these things. Marco, could we go to the slides? Yeah, so this is one of the first papers on blue ball dark matter was by Sony, and I think it was you. So they plotted these various constraints on, this is the, so M is the big scale in the denominator of that effective operator, and little m is the glue ball mass. And so you see the kind of constraints that you get from a whole gamut of indirect searches, experiments. You also get constraints from Big Bang nucleosynthesis, and this is horizontal branch stars. And here is supernovae because what would happen? For very light blue balls, you would be able to liberate blue balls from the star, and it would cause the star to cool faster than it should. Thanks, Marco. Oh, sorry, Marco, I wanted to show another slide, actually. And so the next slide, another example. So this is from David Morrissey and collaborators. They put emphasis on the fact that there's a subdominant blue ball. It's the spin 1 plus minus blue ball, which can actually, if the ground state blue ball is unstable, this one could still be stable because it's got different quantum numbers. It's got negative charge conjugation parity. So they worked out the cosmology of blue balls when you take into account these states as well. And they show you that you could typically quite a range of constraints from, so these are decays of the lowest blue ball that would affect CMB and Big Bang nucleosynthesis, and which would produce these indirect gamma ray constraints. There's one little, yeah, here you would overproduce them. So here's an example where, yeah, I think you want to be living along the edge here to get the right relic abundance, and it gets ruled out in all of these other regions because you overproduce blue balls or you have too big indirect signals. Okay, thanks, Marco. All right. Well, we've gotten through dark mesons, dark blue balls. What's the next thing you could do? Well, the next thing you could do is to add a quark to the model. And if you do that, then you can get dark mesons. You get dark baryons too, but I saved them for last. And so typically, you would think about adding some number of flavors of hidden quarks. And so now we can have mesons being the dark matter. Suppose you have just one, then your bound state is going to be like the eta prime in QCD. It's not going to be particularly light. It's not going to be like a Goldstone boson or pseudo Goldstone boson because the flavor symmetry is anomalous. And so this is a case where you're likely to have so you're likely to, if you just compare it to QCD, you would expect that twice the mass of this meson is bigger than the mass of the glue ball. So this is twice the meson. This is the mass of the glue ball. But the mass of the glue ball will be bigger than the mass of the meson. And so we don't have blue balls decaying. Blue balls don't decay into the mesons. So then you might worry, well, why would I care about the mesons? Because let's see. Oh no, I guess the question is, yeah, how do we get rid of the glue balls if we want the mesons to be the dark matter? But the point here is that we do have annihilations. So there's no symmetry to prevent the glue balls from annihilating into the mesons. And so this is what could deplete the glue ball abundance. You just have one flavor. However, notice that this is not going to be absolute. Yes.
Thanks. How do you know the mass of the blue ball has to be greater than the mass of the dark eta?
Oh, I'm going by analogy with QCD, where we know. Let's see, did I stipulate? I mean, we know in QCD the mass of the eta is like 960 MeV. The mass of the blue ball I mentioned is 1750. So we could say, using QCD as a guide. So at least I know this would be true for SU3. Yes, thanks. Of course, this is not going to be absolutely stable because we always have gravitational decay. There's only one flavor, then we can have QQ bar annihilating into the gravitons. And but this turns out to be a very long lifetime. You can estimate the lifetime to be 16 pi and pi to the fourth over the mass of the dark matter to the fifth. So this is like the age of the universe. Times 2 × 10⁻⁷ GeV divided by the mass of the meson to the fifth power. So you see, it's not a big restriction. You could live with that as dark matter as long as you're interested in mesons that are well below 10⁷ GeV mass. It's not a big restriction. Okay, so that's the simplest thing you could do, just have one flavor. If you have two flavors or more, then things start to look more like QCD. And then you could have something that's absolutely stable, because then we have the analog of charged pions. And then we could have something that looks like charged pions. And this can be absolutely stable, of course. We don't introduce any mediators, because it's got a conserved charge. And this absolute stability, this can be formalized in terms of G parity.
So I'm sorry, you're saying there's some kind of dark U1 here?
No, this is a global. This is just a global symmetry. I'm not gauging anything.
I was wondering about the pion charge.
Yeah, so it just, if I have two flavors of dark matter, then regardless of whether they have any kind of charge, there's a flavor symmetry. And so, if I have a bound state of U d bar, regardless of whether I think these have any kind of charge, I can still call them pi plus or minus. There's a flavor symmetry that they can't annihilate, right? And that's why I'm saying a more formal way of doing this is to phrase it in terms of G parity. Yes.
Would it be possible to conceive of some kind of dark graviton or some modification to the graviton that would allow these these dark pions to decay into gravitons?
No, I don't think that would I don't think it would make sense.
Okay, thanks.
Okay, so to describe the interactions of dark mesons, the standard tool is chiral Lagrangians. And I'm guessing that Hochberg talked about this when he gave you the lectures on SIMPs. Am I right, or did he not? I guess not. So he didn't talk about the more realistic model of SIMS where he was using this kind of dark meson setup. He just talked about the very simplified SIMP model. Okay.
And Yoni is a woman, by the way.
Oh,
No worries.
thank you. I didn't know that. Okay. Yeah, because I've never met her, obviously. Well, so chiral Lagrangians are a way of using these broken flavor symmetries to restrict the interactions. The one that we are used to in QCD is where you have a flavor symmetry for the right-handed quarks and a flavor symmetry for the left-handed quarks, which for massless, if they were massless quarks, then these would be independent symmetries, but it gets broken, and well, the masses explicitly break it, but also the strong interactions spontaneously break it to the vector subgroup. And so chiral Lagrangians tell you what are the allowed interactions that respect this this flavor symmetry. And so you you construct chiral Lagrangians in terms of these matrices. So pi is a matrix. It's a matrix of mesons. And I can write it in terms of the individual meson fields times the generators. Of the you know, the generators of the broken symmetry. Because every symmetry that gets broken leads to Goldstone boson. So this is a way of describing the interactions of Goldstone bosons. So what do you do with this matrix? Oh, and physically, what does this matrix represent? Well, so what happens, what breaks the symmetry, the flavor symmetry, is that the expectation value of this bilinear of different flavors of quarks gets a VEV due to the strong dynamics. And so this is proportional to some scale in the QCD. This is the pion decay constant. And this, so this sigma field is just the dimensionless version of this quark condensate. And here's the proportionality constant. Okay, so so then you want to expand, you're just expanding around this. Oh, and, yeah, sorry. And so typically this expectation value is just the unit matrix. So when we set all the Goldstone boson excitations to 0, then we just get the unit matrix. And what is the chiral Lagrangian? It is F squared, the lowest dimension thing that you can write down, which is consistent with the symmetries, is this object, which gives you a kinetic term, and it also gives you interactions. When you expand sigma in powers of pi, Okay, so here's a term which respects the SU3 left cross SU3 right symmetry. But there also got to be terms that in the real world, if quarks have masses, this is the quark mass matrix. And the mass matrix, it doesn't respect the symmetry, it breaks it in a certain way. But if you allowed it to transform under these, then it would be allowed. So this is kind of a spurion way of figuring out how it must enter into the Lagrangian to break it in a to break the symmetry in a consistent way. Okay, so this breaks the symmetry. And because of this term, so without this term, these would be true Goldstone bosons. All these would be massless fields. They would only have derivative interactions. But because of this symmetry breaking term, they get masses. So I imagine this is familiar to at least some of you, but not all of you. Anyway, this is the standard. If you want to describe the interactions of ions and kaons and whatnot at low energies, this is the standard particle physics way to do it. And so this would also be the way to talk about these kind of dark mesons. And then, yeah, with this you can predict the interactions. Now, to talk about dark matter, we would like to extend this because this is all in a dark sector. How could we get these mesons to talk to the standard model? We want to introduce a portal. Let me just give a simple example. Higgs portal. We could just say couple this kinetic operator to the Higgs field. So then this would be an interaction which would be consistent with the flavor symmetries. Here, I've just subtracted the BEV of the Higgs so that when it gets a BEV, it's not renormalizing this thing. Anyway, this would be a way to get pions to be able to, dark pions, of course, to annihilate into Higgs bosons. And of course, by S-channel Higgs exchange, we could also get other things like W and Z gauge bosons. Okay, so that's how we could get annihilation into standard model particles. And then in this way, we could arrange to get a relic thermal density, usual freeze-out process. Yeah, you could also do it with, you could also couple it to a light Z prime that kinetically mixes with the standard model. Okay, so that's one way to get, yes.
Thanks. I don't quite understand where sigma came from and why we're using it.
Yeah, so okay, so sigma is like an effective field theory description of this quark bilinear, which you can think of, these are the building blocks of a meson. So somehow this expectation value of quarks is related to the mesons. But it's got to be related in a rather complicated way because of the strong dynamics. And so the chiral Lagrangian is a way of using just symmetries in order to constrain what the possible interactions are. And so the claim is this is the most general thing that you could write down consistent with the symmetries. and that's why it works. But I guess the more pragmatic answer is that you can test this against low energy meson interactions and it works. So. And so that's one way you could get the Rayleigh density. And another way is through the SIMP mechanism. And it wasn't obvious maybe from what I just erased, but it turns out if you expand those exponentials, and Taylor expand those exponentials, that Lagrangian that I wrote down, it only has even powers of pions of it. Even this one only has even powers because the odd powers cancel out when you take the Hermitian conjugate. So if you only had that, you would think, okay, there's nothing else I can do to get the Rayleigh density of these mesons, but it turns out that we can get this SIMP mechanism as an alternative. And that's because of something called the West-Semino-Witten Lagrangian. So this is something special. It's a topological thing which only exists in certain theories. It doesn't exist in QCD. But I'll tell you which theories it does exist in after I write down what the Lagrangian looks like. So it's a trace, you have the epsilon tensor, and then it's a trace of pi followed by all the derivatives of pi corresponding to those indices in the epsilon tensor. And so if you count pi's, you see there's 5 of them. This is a topological Lagrangian. So remember here when I wrote SU3 left cross SU3 right breaks down to SU3 vector. More generally, we could say we have some original global symmetry group that breaks down to a subgroup. So G breaks down to H. And what you need is for the 5th homotopy group of G mod H to be non-trivial. And if that's the case, if you have greater than or equal to 3 number of flavors for SUN or SON. And I just told you, but it's not true for the standard model. Well, that's because you need n even. And you could also get it for flavors greater than 2 if you're in symplectic combining group, also for n even. Okay, so it's a little bit of a special thing, but Hochberg and company pointed out that this gives you a nice way of realizing the SIMP mechanism. So this gives rise to 3-2 scattering, and you can estimate, well, you can calculate the cross section, but you can more easily parameterize it by some effective interaction strength over. So I guess one of the things you probably learned is that a 3-2 cross section has funny dimensions. It goes like 1 over mass to the 5th instead of 1 over mass squared. It also has this funny thing that there's 2 relative velocities, and so you have a v squared when you do the thermal average. Yeah, anyway, you can parameterize this, and it turns out that the large n scaling goes like n squared. And it goes like number of flavors to the 5th. And where it gets its dimensions is actually mass over this decay constant squared. Incidentally, this decay constant is around 130 MeV in the standard model, which is not that different from the pion mass. Let's see. So yeah, so when you feed this into the Boltzmann equation, you get your relic density. Let's show some results on the slides. Oh, so I'm surprised she talked about the SIMP mechanism but didn't show this because it's kind of a nice result. What they find is that as a function of the pion mass, so to get the right relic density, and you see m pi over f pi here is characterizing how strong this coupling is. So to get the right relic density, as you increase the mass, you have to increase the other. No, I think I got it the other way around. Let's see. Bigger mass. I'm getting confused which is which. One of these sets of curves is to get the right relic density. The other set of curves is to not have too strong self interactions. And so, and you can't, and this characterizes the strength of the interaction. So you don't want to go above this line or you start losing perturbative control of the calculation. Anyway, what they find is that you have to be in this kind of narrow region of masses in order to get the right relic density and to not have too big a self-interaction cross-section for cosmological constraints. So you got a kind of relatively narrow range of mass predictions for the dark meson. Yes.
Okay, I'll talk about. It seems to be a success of the theory here that our dark meson has a similar mass to the pion mass.
I don't think it's a success. I think it's a coincidence.
Okay, I think that was my question.
Yeah, the question was, is it significant that this happens to coincide with the real world? And
Right.
I think it's just an accident.
Okay, thanks.
Yeah, I'm not going to get anywhere near through my notes, so I'm just going to have to decide when to stop. But I do have a couple more minutes, don't I? Well, so one thing about the SIMP mechanism is that it makes the assumption that the SIMP remains in thermal equilibrium with the standard model. Otherwise, it heats up the dark matter. You know, when you pump the energy of 3 particles into 2, it heats up those 2. You don't want it to get too hot. And so in the SIMP mechanism, they just assumed that there was some portal to the standard model to make sure that it didn't get too hot. And so what is the portal? Possible, we can turn that off. Possible portal mesons to the standard model would always be dark U1, a dark Z prime boson. And to make it a portal, you always just kinetically mix with the standard model. Yeah, so that would be one way to do it. And then you can figure out how does this couple to the pions? You just replace, you do the usual thing. you replace del mu with the covariant derivative equals del mu minus I by A prime mu in the chiral Lagrangian. And then you can calculate what are the interactions of the pions with the Z prime. And then you can have things like this. Z prime, so through kinetic mixing, mix with the photon, then we can have that interact with standard model particles. And so then we can keep the pions in equilibrium with the standard model, which was one of the underlying assumptions of the SIMP mechanism. Yes, I'm afraid I'm out of time, so I'm sorry I was not able to cover as much material as I wanted, but I don't want to keep you here after such a long day. I'll just stop and see if you have some questions.
Is there any?
I think I missed something. So did you say that the West Witten term does not exist in the STEM model? Because I thought you only mentioned that you do have this 2 kaons to 3 kaon process in the STEM model.
I don't think I said that. I don't think
okay,
it
I misunderstood.
exists.
I'm sorry, could you say that again?
I don't think it exists in the standard model.
Okay, but
My understanding is you need the gauge group to be you need it to be n even to get this. SUN has to be even.
okay, I seem to remember you only mentioning that there was this 2 kaon to 3 kaon process in the STEM model.
I don't remember ever saying that.
No, I remember Uni.
She said it. It's in the
Yeah.
standard model. Oh,
Yeah.
okay. Maybe I have to recheck that then.
Thanks.
My understanding was it was not there, but.
Okay, so thank you very much, Jim. Thank you.